When we've considered a system thus far, we've considered it from a macroscopic point of view. This idea is that we're considering the object as a whole. There's a mass of the object as a whole, and this object is moving with a velocity. Considering this type of macroscopic object, we've defined its kinetic energy as 1/2 mv squared, where here m is the mass of the entire object, v is the velocity of the entire object moving in one direction. From a microscopic or a nanoscale point of view, however, the object is actually made up of billions and billions of tiny atoms. Each atom is oscillating and has its own kinetic energy from its own molecular vibrations. The molecules are held together by molecular bonds. These molecular bonds have a neutral length to them, a desired length to them. Stretching and compressing them gives them a potential energy that can be modeled as a spring energy between these objects. Thus, inside the atom, at a nanoscale, there is a kinetic energy due to the motion, due to the vibrations of the molecules in the object. There's also a potential energy due to the stress and strain on the molecular bonds of that object. This microscopic kinetic energy and microscopic potential energy combine to count as the thermal energy of the system. And thus we define the thermal energy of the system as the combination of the nanoscale kinetic and nanoscale potential energies of the system. When we consider two objects sliding against each other, we look at a situation like we have here, where we have the object that's moving relative to a surface, for example, that's not moving. In this sort of situation, the object has kinetic energy, and the object also has thermal energy, because any object is made up of atoms, and those atoms have a certain amount of base energy. So any object will have some amount of thermal energy. For the surface, the kinetic energy would be zero because the surface isn't moving, but that surface would still have thermal energy to it. As our object moves past the surface, we have bonds that form between the molecules of the surface and the molecules of the object and the molecules of the surface. As they slide by, there'll be some electrical attraction between the two. We'll see in later modules more detail of that, but they will want to form bonds. They won't want to slide past each other. And as they do slide past each other, these bonds break, which cause more vibrations within the molecules both of the object and more vibrations within the molecules of the surface. In that case, these vibrations are an increase in the thermal kinetic energy, the nanoscopic kinetic energy of the system. That increase in the kinetic, the microscopic, the nanoscale kinetic energy, that increase in energy will eventually be spread out through all of the atoms via these molecular bonds that act like springs, and that will end up increasing both the microscopic and the nanoscale potential energy of the system. Together, that is increasing the thermal energy of the system. Basically, both the object and the surface both have increased thermal energy. Both of them are getting hotter because there's more molecular motion due to the interaction of these bonds. This increase in thermal energy comes at the expense of the the kinetic energy of the original system. So basically, what we have here is that the object is losing thermal energy. It's losing thermal energy due to this rubbing between the object and the surface. And there is a increase in thermal energy that is the opposite of this loss of kinetic energy. Basically, the loss of kinetic energy of the object shows up as an increase in thermal energy. However, this increase in thermal energy shows up in both the object and in the surface. And showing how much thermal energy goes to either one, is a little bit more complicated. We'll see that a little bit later when we get into looking at thermodynamics and the transfer of heat energy. The point that we're trying to see here is that kinetic friction is a dissipative force. That means that it's dissipating the macroscopic kinetic energy of the object. It's taking away that object, the energy of that object. It's dissipating that energy, but the energy doesn't disappear. It doesn't just go away. It becomes thermal energy by heating up both the object that is moving and also the surface that is providing the friction. That's why, for example, if you push your hands together and rub them together, Mr. Miyagi style, you'll feel that both of your hands become warmer. If you imagine one hand is the moving object, the other hand is the quote-unquote surface that's not moving, you'll feel both of them get hotter due to the friction between the two. The way we quantify the loss of kinetic energy or the increase in thermal energy is looking at the work done by this dissipative force. If friction is a dissipative force, then it must do a work that is the force of friction times the displacement. This is because we've dealt with friction, we've assumed it to be a constant force, and so it'll follow the simplest model we have for the work done. So in this sort of system where you have a block that's being pulled across a horizontal surface by a tension, that tension is being used to overcome a force of friction. We have a constant velocity here, so the net work is 0, which means that the work done by the tension is the negative of the work done by the frictional force. And so we can find what the work done by the tension is, we can find what the work done by the frictional force is. This work in this situation, the friction is in the negative direction, is the opposite direction of the displacement. And so the work done by friction is a negative value. And what that means is that is energy that's being taken out of the system. It's being taken away from the block. And energy can't be created or destroyed. Energy has to be conserved. And so where does that energy go? That energy that's taken away from the kinetic energy of the block goes into the thermal energy of the block or the surface. And when the energy becomes thermal energy, these dissipative forces are increasing the thermal energy of the system, but they never destroy the energy. The energy has to be conserved, but that energy is lost to us. It's not usable anymore. It's thermal energy in the system. And while it exists at a microscopic level, it is gone in the sense of being useful to us as a macroscopic kinetic energy of our block.